let me highlight that Tan is only here for today. So if you want to grab his for comments, questions, today's the day too. So thank you so much.
Thank you, the organizers, and thank you for coming in. Today I'll be talking about retrospective search. This is how we coin it, although the idea is kind of relatively simple. We want to talk about searching for something, and the goal is to find that something that is going to be best for you, and then just pick that one out. What could be an idea? Maybe we're trying to find the efficacy of a drug, and we're trying to increase the dosage gradually until we find that, you know what, at some point maybe it became too dangerous for the patients, and we go back to the most efficacious level. Or maybe it could be the case that I'm trying to tweak around the model until I actually get to something that I can solve around, where I'm doing incremental changes where I can get a solution. Another search would be if we were to actually try to search for gold, what you would get is a mineral vein that will be dictated by the Department of Agriculture. And you just go searching through that mineral vein until you, by digging small exploratory wells, where at some point you're going to decide, okay, I think this is where I'm going to develop the whole actual mine and then exploit that mine forever. Same is true for policy experimentation. Maybe you want to start with, I don't know, casual Fridays, move a little bit more to casual Fridays and semi-casual Thursdays, and then eventually decide halfway casual is the best one for you. And finally, it could be something as simple as online shopping or real life shopping for this example. I woke up, I walked down the street where I'm gonna get my bagel and coffee. I walk down the street until I find a place that I'm going to like, which was a Bagel Street Cafe. And then I decide that's the place I'm going to get, come back, purchase from there. And now I'm happy enough to actually talk to you and fed enough to talk to you. So there are two main features that we want to kind of highlight within this search. The first is correlation, because if I'm digging down through a mineral vein, how much gold I find is kind of indicative of how much I'm going to find immediately in the adjacent plot. Or if I'm looking for restaurants at the street, there is going to be some sort of neighborhood effects that's going to tell me what kind of restaurants that I'll be seeing. If we think, for example, online shopping, I'm going to look through, let's say, a clicker on Amazon, and then Amazon is going to tell me customers have also looked to something similar, which I expected to be a clicker and not something else entirely. Second thing is, I'm going to also choose my speed. I can try to rush through the street to get my bagel, or I could actually slowly, leisurely take a walk and decide which one I'm going to actually pick. And both of them are going to be decisive in the eventual outcome that I'm going to choose. So our question is, how should we conduct a search like this? What pace should I be going through? And what am I going to eventually pick and how I'm going to stop? So the correlation, we're going to actually borrow from Steve's idea, and we're going to think about the set of outcomes to be a realized Brownian path. So the street is over there. I don't know what's in there. There are some qualities over the restaurants that I might see that I'll eventually pick through. And I'm going to assume our search is going to be incremental. This is admittedly a restriction because maybe I actually take an Uber. I realize that half of the street is not relevant for me. But for some other applications, it's going to be a little more natural. For FDA, it's going to actually require you to test the dosage in given increments. If you're doing mineral exploration, you're actually going to have to move to your digging machine incrementally. It's not going to teleport from one place to another. And then the search speed we are going to capture by actually choosing costly variance. This allows us to think about variance in two terms. I'm going to be mostly using the term speed in terms of actual speed, but another way to think about it is actually my breadth of instantaneous search too. It could be that when I'm looking for a clicker, how many O's I go through of the Google could be my instantaneous variance choice as well. And finally, we're going to assume obviously perfect recall. After I search through the street, I'm not going to forget what I saw at the beginning of the street. I mean, I might, but we're going to assume the decision maker is not going to do that. And they're going to go back and pick the best choice that they will see. Turns out we're going to actually have a U-shaped search speed. Now that U might seem a little bit odd at this point. That U is going to be related to the breaks we might have in the search. And there are two breaks that are relevant for our search. One is going to be a breakthrough, where we are going to find a new best outcome. So I saw one bagel shop, and then I found a new bagel shop. That's going to be a breakthrough for me. And then the second one is going to be a breakdown, where I say, you know what, I ended up in some weird neighborhood. Maybe I shouldn't be actually going forward. And then I go back and pick up my food from somewhere else. That's going to be our breakdown. And our search speed is going to be U-shaped in terms of where our breakthrough and breakdown levels are. And notice these are going to be things that we're going to be carrying over as we see more stuff. And the stopping rule is going to be a relatively simple stopping boundary, which means we're actually not going to, I'm going to use the term boundary instead of a stopping region, because stopping boundary, I will say that once we see something that's bad enough that we're going to stop. That's distinctly different than satisfying behavior, what, for example, a bandit model or like independent search would tell you, where once I see something good enough, I'm going to stop. Because in reality, we see that you don't actually see something good enough and stop. You usually actually decide, I don't know, sampling 5 prices or sampling different restaurants and go back to the best one you might have seen. And then I'll also talk about the application, given that the solution would be a little, is going to be surprisingly simple. We'll be able to actually embed the search model into a contracting environment. Instead of me searching for a restaurant, I'll actually hire someone, pay them a wage, and give them a commission to do the search on my behalf. This, of course, is going to be the case, for example, you want to sell your house, or you want to be buying a piece of art, or you're actually just trying to find a new innovation where the university is paying you a wage, and eventually they'll get a chunk out of the new patent you get. Those kind of contracts we will be able to characterize completely with this methodology. Now, in terms of literature, well, some of the literature is actually already in here. It's related to Pandora's problems, obviously, because there is some search and we're searching until we find something and we pick the best option. And there is some relation to experimentation, although there is not exactly experimentation going on. We're not learning about some unknown attribute and trying to make tests about learning about it. This is actually some realized Brownian path where we are trying to find the maxima for ourselves. And that already is going to be somewhat related to the optimal stopping of a diffusion literature in math. So this bit I'm going to leave to Steve to talk about a little bit, but to me, at least, he is one of the forefathers of this actual modeling choice of capturing correlation in search models. So today I'll be first talking about the model and give you the optimal policy. And then I'll be describing the contracting and conclude. Now, with the idea in mind, let's try to actually formalize this a little bit. We're doing our search in continuous time. You might want to try to think of it as a discrete version of searching through a random walk as well, if you want. Although there'll be some gaps in that idea where you'll lose some tractability if we go that way. So the basic set of prospects is there is a street and I'm running at speed sigma t through that street. I'm going to assume for now we start from 0 expectation because that's also my fallout option. I need to eat something which has utility 0 if I don't eat anything. At every point in time, our agent is going to choose their speed, or you can think of it as ambition or breadth. And we are going to assume that agent cannot stop because if you're just idling, you're letting time run by while your hunger is accumulating. And cost of actually walking faster is going to be increasing. It's going to be twice differentiable and convex. Sometimes I'm going to assume it's log convex to give unique predictions, although it's not necessary. And the perfect recall part. From whatever I have seen so far until this point, the best option is going to be the maximum that I keep track of. Again, we need to somehow start with the initial point, and there's no harm in assuming that M0 is equal to 0. So I didn't come with a cup noodles in my bag. Just to give a little bit of a picture, if this is the, for example, utils or the payoffs I would get from the different restaurants in the street, there is no, this is the pre-realized path of the street, somewhere down, I don't remember the name of it. Then the maximum has some peculiar properties, if you look at it. First of all, this is a graphical glitch. Maximum is actually almost surely constant. Most of the time, it's going to be constant. When you really zoom on in here, it's going to look like this inside there as well. Second, obviously, it's increasing, which is going to be kind of useful for us to think about the problem. One thing also about maximum that's kind of nice is that if we actually use a constant search speed without an extra E, then the maximum is proportional to sigma. So this kind of allows us to have a good interpretation and compare it to, for example, exponential search models. If you're doing exponential search in labor, you see that if you increase your speed or effort, every outcome you're going to get is going to be better, and they're going to be potentially coming at a faster rate. Here, what we end up with is that if I'm exerting more effort, then I do expect to find something that's really better, and that's proportional to the sigma that I have. But not everything is going to be better. I'm really just searching with a wider variance. Second thing is, even though the maximum process by itself is a rather weird process that's almost constant everywhere, if I look through arbitrary breakthroughs, those are going to actually happen really with an exponential distribution. So we're kind of getting that good news or breakthroughs are coming through some exponential rate, but we're not assuming the underlying thing is actually exponential and independent from past or what we have seen before. And the goal of our agent is relatively simple. Our agent is trying to maximize the maximum that they will encounter. That's going to be discounted by some discount rate. And as they continue their search, they're accumulating costs until they actually stop, again, discounted with the discount rate. Subject to the actual search process that we have is just determined by our speed, and the maximum is just as we have described. We might put a utility function for M as well, which I'm going to hopefully talk at all the way to the end. But for the basic premise, we're going to assume that the process we're searching through is really capturing in terms of utils, so we're going to avoid risk aversion for now. Our agent has two choices to make at a given time. The first is obviously tau, and then the second is the sigma t, where sigma t obviously has to be an adapted process, tau has to be an adapted stopping rule that we can pick through, and they're also connected with each other too. So we're doing control and stopping jointly at the same time. Now, to think about the assumptions we made, with independence, recall is unimportant. Actually, what you're going to do is you're going to set a level, and then the moment you see something above that level, you stop. Very easy, but not really good with empirical evidence of how people have done their search. And it's going to be satisficing behavior. If we do not have recall, then actually we're searching through Brownian motion that has no drift without recall. I'm paying cost to have an expected increase of util of 0, I'm never going to do that. So recall should actually be the case that it makes it sensible for me to continue the search. If there is actually drift, which we didn't assume, where actually we think that the street is getting better as we go along, then I either stop immediately or search indefinitely. It's not going to make a lot of difference. We can also add risk aversion without recall. If you add risk aversion without recall, then again, you might still have a simple decision of when to stop. Again, we will also still require some positive drift. We're assuming no drift for the relevance of applications. First is if I'm doing some sort of research, if I'm just doing, think of this as really generating ideas, and the Brownian motion is capturing the new idea with sigma, the amount of tweak I do to my idea at a given point in time. If there is drift, then that means mere passage of time is going to give me better results. That means if I actually look at, for example, Amazon look long enough, then it's going to show me their best product. It's not going to actually show it to me from the get-go. So just I should pass through the first few ones ahead. Second, you might think about me actually searching about an ordered list of tests. If I already know something far into the future is better, then I should just start from there, not from somewhere in the beginning. And we actually can accommodate fixed drift as well. It just makes the analysis a lot more cumbersome. It's not that it's impossible to incorporate. It's just a little odd and makes our calculations pretty bad. If we were to only add the drift, then we get Pesquier's other paper. The first one was the optimal stopping of the maximum. This is the optimal stopping, optimal control of drift. The result is a bang-bang result. It's not terribly interesting. You either maximize your drift or minimize your drift, and that's all you have. And again, effort is increasing all outcomes if you're controlling drift, whereas we want to capture that effort is actually increasing the best outcome you will see, as opposed to everything that you will see. Okay, so let's get back to the problem. We were talking about the strategy of being composed of two elements, the choice of search and the stopping time. And both in principle might depend on the entire history of MT, XT, and even calendar time if you want to do it. But first, let's make our stopping rule a little easier. If at any time it's optimal to stop at the M and X, then if the current realization is lower with the maximum being higher, with the maximum being the same, I should also stop. It's quite intuitive. I have the same fallback option. I'm in a worse part of the town. So if I was stopping at a better option, I'll stop at the same point. Second, if it's optimal to start the problem at 0, 0, then it's optimal to continue at a new maxima as well, because what I have done is I have added M to my pocket and I just restarted my problem altogether. So that means actually it's never optimal to stop at a new maximum. Then the only way we are going to actually stop is when we something bad enough. In terms of research, it's going to be the case that I'm doing this drug research and I see it's getting better and better for my patients. I'm not going to stop. I'm only going to stop that if somebody is going to end up dying, then I'm like, okay, maybe this is really not going to work out. I should go back and go use an appropriate dosage for these. And a simple way to represent a stopping rule of this form is just assuming there is some sort of continuous function such that when the current observation is below this G of M, we are going to stop. We do show that this function has to be continuous, but it's kind of easy if you think about it. Everything is smooth. There cannot be any jumps in there. Now that we have a function, let's try to actually depict what it looks like. A simple function. If G of M is M minus 2, That's what it looks in terms of m versus g of m axis. But in reality, it's going to tell me that if I have a realized path, then this g of m is actually also following the realized path of g as well, m as well. And I'm going to stop, for example, at this point. Whereas if I were using m minus 3 over this path, I would not have stopped. If this were a more complicated function, then these differences would be changing as we go along. It's constant in here, but that's all it's going to change. It's still going to be some sort of shifting of the maximum function we see. So now that we have the basic model, let's actually describe what the optimal speed is, because it's going to be quite easy. If we have a continuous stopping boundary, then the optimal search speed is identified uniquely by this equality. Let's try to actually ignore this elephant in here and look at the right-hand side and the left-hand side. This is telling me that the optimal search speed is dependent on both the level of the costs as well as the margins. This kind of makes sense because if I'm changing my speed, I'm changing both how much my marginal cost is going through, and for whatever my optimal stopping rule is, I'm also changing how fast I'm going to that stopping rule. In terms of time, I'm paying that C, whereas in terms of increase in speed, I'm paying that C prime in there. Now, where is this creature coming from? This creature is coming from the fact that we had the brakes, right? And this is actually the brakes we have. I'm either going to try to reach a new breakthrough, or I'm going to try to reach a breakdown. Because if you really think about it, the search I'm doing at an arbitrary point is going to not change my maximum. It's always almost the same. All I'm doing is kind of accumulating costs until I reach a breakthrough or breakdown. So the goal is to somehow capture how that is going to affect us. And that is going to tell why we get that U shape again. As I'm kind of approaching, for example, a new breakthrough, then I'm thinking, you know what, my maximum is about to change. Then the expected time I'm going to spend trying to reach a breakthrough is not going to be that high. I can try to speed up. If, on the other hand, if I'm somewhere smack in the middle of the breakthrough and breakdown, then I'm thinking, well, the problem is pretty stale. I'm either going to break down or I'm going to I'm going to do a breakthrough. Right now, if I speed up, it's not going to help me because I also have discounting to take care of. Instead, I should potentially try to save on my local costs right now, where I'm going to try to slow down in that part. Yeah.
The question is about the previous slide. Is G of M always M minus a constant or no?
It will turn out to be so. In general, it needs a proof though.
It is.
As long as you have risk neutrality, it is. Now, here comes the part. If C is log convex, then this is monotone. Then you actually have a unique solution. It's obviously a sufficient condition. There could be many other conditions that you can come up with that guarantee a unique solution here. And another thing to realize is if there is no discounting, we get this part, then our search speed is going to be constant and independent of the entire thing that we have seen. So if you're doing some sort of search where discounting really doesn't matter, like me searching through for a bagel, it's a relatively short amount of time. I'm not gonna have significant discounting over there. Then my optimal speed is constant and completely independent of whatever I have seen as far as the options and what the best and the current options are. And this bit is actually something you can really just open up your handbook of Brownian motion and find it in closed form. because it's a standard Brownian motion escaping. There is no more speed in there. And it has a relatively ugly form, but it's at least something we know. So that equality is actually uniquely pinning down the entire search speed. And one thing that, again, that I have said is that it's going to be constant when there is no discounting. Another thing that I should also say is that if you look at the formula beforehand, you will see that expected discounted time is also approaching 1 as you approach the boundaries. So that means actually, even if we have discounting, towards the boundaries, we will have the same speed as if we have no discounting. So what does this mean? If we look at this weird clown face looking thing, we see that no matter what our discounting is, it's only going to have an impact when we are away from the boundaries. And it's a mechanical effect. It's just saying that the relative path is not really saying much. The difference is purely how fast I'm able to escape from this breakthrough breakdown cycle. Okay, and we see that this is also somehow relevant to some behavioral observations you might have, which is the goal gradient hypothesis, where you're going to exert greater effort when approaching a goal or when approaching some kind of breakdown. Instead of a behavioral explanation, here we end up with an analytical explanation if you buy the assumptions of the model so far. On the other hand, if we think about the constant search speed, that is also pretty evident that you can see. Many companies do not fluctuate their research and development expenditures, regardless of what they are actually finding through. And in fact, again, mineral prospecting, it's one of the award-winning procedures. You might actually hit a very promising vein or a very promising exploratory dig or a very bad exploratory dig until you run through the vein and until you give up. You're supposed to actually dig at the same depth, according to Zilkin. So let's try to get a little bit of a better intuition. If we're kind of looking at the speed, it is really kind of, we're looking at distance in time. So if there was no discounting, this is really how much I'm paying per second. And this is how fast I'm running through. And in fact, if you maximize this, you end up with the sigma 0 that we end up in here. It's kind of a misleading intuition over there, though, because that is going to minimize cost per distance in time at every point. The idea is you're trying to actually minimize the time to escape. If you have no discounting, minimizing your cost per distance is also minimizing your time to escape. That's why this is kind of misleading, but easy to see where the formula comes from. Now let's think about the stopping boundary. And the stopping boundary is exactly what you have said. It's going to be identified by a constant where it's going to be m minus dr, where this dr is going to solve this particular equation. It might look ugly, but if you like squint enough, you'll see that this is the expected discounted time, again, the Brownian motion escaping through. And d0 is actually showing up because our speed at the boundaries were actually independent of the discounting we had. So it's a closed form, something you can also do calculus on. It looks very bad because it has sins in it, sin h and cos h in it, but I think it's good enough for an optimal solution, optimal stopping problem. One thing we want to kind of also mention is that when you have a boundary that's actually linear, it's called a drawdown. I'm going to observe the outcomes, and whenever I fall dr below, then I'm going to decide that it is time for me to stop. It's as if I have drawn down of a constant distance, hence the name drawdown in there. As R increases, dr is going to decrease, which is saying that if you're getting more patient, your drawdown is decreasing. So you're going to actually demanding a better and better path. And again, so the picture I have shown you was not a random picture. It was actually some optimal solution from what we could have seen before. Another thing is when the discount factor does not exist, then the drawdown is extremely simple. Why is that true? The intuition is also quite simple. If we actually just push our current state and maximum by a constant amount, then the problem hasn't changed. We actually saved everything in there, which means the gap has to be constant. But then the moment we know the gap has to be constant, then we can use the speed solution we have to try to actually pin down what that gap is. And that is very dependent on how fast we are going. So that is kind of the addition you will see from in the regular optimal stopping literature, your speed is given to you. Whereas here, your speed is actually governing your entire stopping rule as well as your payoff. Okay, now let's think about allowing for risk aversion. One particular thing is that the speed equation that I have shown you is completely independent of the shape of the utility function. So in the sense that if I'm given the same drawdown rule, that's a big if though, then the speed is not going to have any, the utility function is not going to have impact. And the idea is simple. I'm still trying to escape. And if I'm escaping, I'm only accumulating costs. Remember, our utility was going to come to the maximum, not to the cost part, because we already assumed some increasing convex costs that were separable from the payoff that we were going to get. So for a fixed stopping rule, then utility is irrelevant, which might be an application you might actually try to put into a model. Because if, for example, my boss tells me when I should quit, then we're able to predict the speed you're going to do, regardless of we know your utility function or not. On the other hand, if we do have nonlinear utility though, suppose we actually have some risk aversion, then there is going to be some level where getting high enough means I don't want to experiment anymore. That means there is going to be some satisficing level that will tell us when to stop. And then there is going to be a boundary below where the stopping region is a flat line and the boundary that's approaching the flat line. So as our maximum increases, this gap is going to slowly decrease and you will have a satisficing level with a boundary that will determine your optimal stopping. In general, there is a technical hiccup in here where the differential equation for solving the optimal stopping boundary turns out to be a Abel equation of the second kind, which are generally intractable. But if you have CRRA utilities, then we do provide a optimal parametric solution in the online appendix. So now that we know the speed and the stopping rule, we also need to know what is the search going to yield, what kind of bagel I'm going to end up with. And for that, we're going back to the case of risk neutrality. The first thing we can actually show that the expected payoff from optimal retrospective search can be identified in closed form. Again, as a function of the drawdowns, which are functions of the optimal speed that we have identified. What am I doing on time? The other thing is the expected bagel I can also find it in closed form for the case where R is equal to 0. Expected search duration, again, I can also find in closed form for R equals to 0. When R is greater than 0 though, unlike the payoff, these are only identified in terms of their joint moment generating function. So you can do comparative statics with it, but putting them down in a closed form requires some additional assumptions on the cost function. Now, the expected maximum value is kind of intuitive because Brownian motion is a martingale, and we have a drawdown. That means the moment I stop, the gap between my current value and the maximum is exactly the size of my drawdown. So that was easy enough. That tells you what my expected maximum is, given that my current x is. Expected search time is the part where the sigma part is kind of speeding up our search duration, tantamount to a sigma square in the increase. And then the expected search time of the drawdown to the speed is kind of square rated. This one is not a good explanation in terms of intuition, but that is going back all the first thing I said about the exponential arrivals. And that's why you're kind of ending up with the low looking a little bit of the exponential coming in there. There are no general comparative statics that you can get in terms of costs because you can increase marginal costs, but keep the cost level the same. We don't know where it's gonna go. But for inpatients, then you do actually have solid comparative statics. So now we have the entire result of the search. Everything we might be interested in, hopefully, identified in closed form in terms of the parameters of the model. But then we can actually try to apply it into a contracting model too, because now that we have everything in closed form, let's try to do that. And in fact, mineral exploration, going through a vein, is actually done by a financing firm hiring a mineral digging company. That's not the official term, but whatever they do. And in the end, they'll get some ratio of the profits. And as long as they're doing the search before they develop, they're being paid a wage. Same is true for, well, maybe not us, but people provide, maybe the computer scientists, where they actually provide patents and the university is going to get some share of their proceeds. And similarly for art dealerships, I can actually try to give negative wages. I might actually have my art shown in some gallery, pay for it. And in the end, when it's sold from there, there will be actually a commission that the gallery is going to get. So what we're going to do is an agent is going to do a retrospective search. Principal is the residual claimant. So we're going to get the rest of the commission and we're paying the wages. And it's actually kind of similar to the rules suggested by Agion and Troll. Our agent has an outside option of 0, can quit anytime. For simplicity for here, I'm going to assume there is no discounting, but in fact, you can add discounting to the agent and it's gonna make almost 0 difference. It's this part where the discounting is going to matter because then these two we only identify in terms of their joint moment generating functions. But you can actually have an infinitely patient principal contracting with an impatient agent to do their search on behalf of them. But we know agent's problem. Now all has changed is we decreased the costs by W, but the margin hasn't changed. And we're giving them a fixed ratio alpha, which is a linear transformation of the utility function as opposed to a nonlinear one, which just as we have done before, since we assume there is no discounting, we can actually solve the agent's constant search speed immediately. And also the agent's optimal stopping boundary. But given that we can actually solve for these two, that means we can actually solve for these two as well in terms of what the agent is going to do as a function of the wages. And what we see is that there is going to be a constant search speed that does not depend on the commission as a whole. So you might give me 90% of my winnings or 10%. It's not going to tell me what my optimal search speed is. It is going to tell me how fast I'm going to stop though. On the other hand, the boundary is going to depend on both the wage and the rate we are getting. And this is also again saying that the optimal stopping rule is very inherently tied to the optimal control problem and not the other way around. And in fact, once we solve for these two though, the principal problem is almost static. This we have now a closed form solution for. This we have a closed form solution for. We're going to find the W and alpha to maximize what the principal does, which tells us this will be the optimal speed and the contract that we're going to pay. And I'm almost out of time. Excellent. So what we have done is that we ended up with a retrospective search model that is with correlated observations and experimentation. And the optimal policy turned out to be U-shaped with a simple stopping boundary. And this drawdown stopping boundary is actually quite evident in empirical research of people shopping through Amazon or not, where the simple case of independent price sampling does not seem to explain what's going on. And it makes sense. If I'm actually looking for the price of a book, it will be correlated what I see in Amazon to Barnes & Noble or even different sellers across Amazon. Not somebody is going to price a book for 100 and another for 70, although that might be the case for the Handbook of Brownian Motion that I previously mentioned, just because it's out of print. And the second thing is the analysis is quite tractable. I mentioned commission search, but you can also think about constraint search, where your principal can, in addition, put, for example, deadlines, or they can, in addition, say you have a satisficing rule and everything going through. The agent's part is quite easy. You're just kind of deconstructing what's going on through. Another bit that we have kind of worked through with quite a bit is where you're doing a joint search. Suppose you gather a group of people, they're going to think about ideas about how to do dynamic information acquisition. And everybody is pitching in until some of them are going to decide, you know what, I'm going to write a paper on my own. Or maybe they're going to say, let's jointly write a paper. We're just going to quit from this conversation and go to a corner and start scribbling down a model, which is the case we actually searched through with Doruk Çedemen. Another beauty of that is it can also serve for a foundation for a matching theory, where suppose you have pairs that are going to be doing jointly a search like this, where they are both contributing speeds and they can actually quit on their own to get a maximum. Then this gives you, in terms of your own cost functions, a complete preference order on potential pairs you might have. So you can use this as a foundation of kind of a matching theory for, I don't know, professors and PhD students or potential co-authors, and get again, a quite tractable foundation going back through only to the cost function. And that's the end. Thank you so much.
So thank you, Rami, for this talks. And I think that we will be back with our team. Doctors, cocktail time.